Hi again, it's been a while. I started this course using the book of shaders as a reference. Personally, I learned a lot from it, starting with color, shapes, transformation, and noise. I've tried to present all these concepts in various video tutorials. However, we have practically covered all the topics in the book, and now we need to move on to new subjects. But I have to say that it's not just about adding a third dimension and using 3D shapes, but delving into a whole topic called the rendering pipeline. The rendering pipeline is about how 3D graphics are finally rendered on the screen. I believe that by exploring this topic we can move on to more elaborate shaders and very interesting effects. The rendering pipeline is complex and extensive, and there are complete courses dedicated to it. I highly recommend this particular course on computer graphics. It has everything you need to know about the rendering pipeline. Now, I want to present to you the Rendering Pipeline Museum. It's the idea and the way I conceive shaders based on my experience of over a year. Its focus is in Godot and the required elements for programming shaders on it. So let's start with the physical device where the GPU that processes the graphics is located. The most common is the dedicated card, which has a dedicated memory for video called VRAM. The GPU built in with a processor that doesn't have VRAM memory and therefore relies on system memory, which is slower, and mobile phones, which in particular I find very interesting, that low-end mobile devices actually have the capacity to load complex scenes and even handle simple shaders. Now, here we have a diagram of the rendering pipeline that consists of several stages. In several of these stages, we actually can't do much. In the particular case of Godot, we don't have access to the tessellation process, which allows for dynamic subdivision of geometry like Unreal Engine, for example. However, we do have access and complete control over the vertex and fragment transformation stages. Now, here we have a simplified diagram where we only have access to the vertex stage and the fragment stage. The rasterization process is controlled by the GPU. This process is very similar in the Vulkan and OpenGL APIs that Godot offers. Now, let's move on to the first stage of the rendering pipeline, which is the input assembler. In this stage, the APIs connect with the GPU and send the same data to the rendering pipeline. The data consists of geometry, textures, and shaders, which are compiled initially before use them. Now, among the data we can send to the GPU and its rendering pipeline are predefined mesh primitives available in Godot. We also have external data like this model created by the artist Kenny, which is made in an external application. Next, we have the third type of data that is dynamically generated through code, such as GDescript in Godot. Typically, this type of geometry data is used to generate infinite and dynamic terrains. When I say data, I mean that it contains vertex position information. For example, here we have 8 vertices that define a cube. Then we have 6 faces of the cube, with each face formed by 2 triangles. In total, we have 16 triangles, and triangles are formed by connecting the vertices in a specific order that determines the direction of the object faces. We define the GBs and finally process all the data to generate the geometry. The GPU primarily works with triangles and handles them in a very efficient way. Now let's move on to a very important topic, that is coordinate systems. These are the different transformation stages that the geometry goes through from local space to screen space. We'll use all these spaces later in different shaders, depending on their functionality. To transform the geometry between the different spaces, we use transformation matrices. These transformation matrices are model matrix, view matrix, and projection matrix. The model matrix and the view matrix are arranged in the following way, with 3 column vectors representing the different XYZ axes, and an isolated 4th vector representing the displacement vector. The matrix is in column major order, meaning it is stored vertically, but in programming we access it horizontally. Let's see the local transformation in local space on the external 3D model. As you can see, there is a wave-like motion. It's distorting the model on its x-axis. It doesn't matter that the model is rotating. Here you can see the shader. I am just applying a sine function, very similar to the deformations I used in the fragment, but this time modifying the vertices with the vertex function. The rotation is done using GDScript, which you can see is very simple. This to demonstrate that external rotation of the model doesn't affect the local space. Now, let's see a world transformation using the world space. As you can see, I am applying the same sine wave, but in this case, the wave is aligned with the world space and no longer uses the local space of the object. Here is the shader I am using to deform the plane. As you can see, the same function, but with the difference that I am multiplying the vertex by the model matrix. This matrix contains the world coordinates, and let me deform the object using those coordinates and not the local coordinates of the object. The 3D objects have their own local transformation matrix that was originally used to build them, with a 3D application such as Maya in the case of this model. This has to be taken into account when applying transformation to vertices. Let's see the next space, which is the view space. In the view space, the center of the universe is the camera. Everything is relative to the camera. The distance of the vertices are not measured on their local transformation, neither to the origin of the world, but to the origin of the camera. This is all because in video games and applications, there is the movement of the camera, but the concept of camera does not exist. There is only a 0 point where everything will be processed into a final image. As you can see in this space, the camera is fixed at the origin and always pointing to the -c axis, and when there is a movement of the camera, it transforms the camera to its original position by dragging the objects and then transforms them to fit the origin position of the camera. In other words, any movement or rotation of the camera will have its inverse operation on all objects in the world. Now we're going to see the next effect of fading. This effect comes by default in the spatial material. I just converted to shader, and it's only a matter of applying the Z distance of the vertex that is in view space to the alpha property. If I clamp these values from 0 to 1, I get a better result. Also, I can apply a smooth step to get a range of distance on the effect. I've applied the billboard effect on this model. It seems to work better on planes and quads. The object follows the rotation of the camera, as you can see. This effect can be activated in the spatial material. It works by creating a custom matrix, copying the camera rotation from the inverse view matrix, and in the fourth column we leave the original position vector of the object. Then we take into account the original scale. Now, let's go to the next space, which is the ellipse space. Here we discard the geometry that is outside the limits of the view frustum of the camera. The view frustum is a box that limits the objects that are visible to the camera. Its shape changes between orthogonal projection and perspective projection. Here you can see the variables that determine its shape, which are the same as those found in the projection matrix in the form of trigonometric equations. So the projection matrix isn't similar to the transformation matrices shown before, which correspond to linear algebra transformations. Even the corresponding basis vector doesn't exist. The projection matrix can handle the projection from view space to clip space and back using the depth map. We use the projection matrix to linearize the depth map for artistic purposes or to measure the exact distance from vertices. This is the depth map, and it is incredibly powerful for creating visual effects. For example, in this sphere, you can detect the collision between the vertices of the sphere and the cube. In the example I uploaded last time, I am using the depth map to alternate colors depending on the distance of the objects, and to generate foam where the plane collides with other objects. Here is the shader that I am using to get the depth map. There is a node in Visual Shader, Proximity Fade, to get the depth map quickly. Here is the code generated automatically. I have this function here that does exactly the same. The key aspect is that we apply the inverse projection matrix to go from clip space to view space, getting the x and y coordinates of the UV screen and the z coordinate from the depth map. The division by the W factor gives you the correct depth map in its linear form. Now, let's see a short overview of the rasterization stage. As I mentioned before, this is an extensive, complex, and multi-stage process. The first question that came to my mind when I first learned about the rendering pipeline is how to capture an image. How do you go from a three-dimensional geometry to a two-dimensional plane? I mean, in the human eye, there are specialized cells to capture the amount of light and tone, and finally transport this information to the brain through the optic nerve. In a digital camera, there is a specialized sensor. What you see below is my attempt to draw a camera sensor, and it stores the image in a digital form. But in OpenGL, as we saw before, the concept of camera doesn't exist. What it really does is to cut out the geometry in the clip space, and then process the information that comes from the textures and geometry directly in different steps. One of the steps is sampling, that is to divide the triangles of the object into a grid and start taking samples of the colors. For example, in the illustration above, from each of the squares in which we divide this triangle, we take a small sample of the central point. But this sample will not be correct if we take the exact color of the triangle or the background color. We have to subdivide the grid to take 4 samples, combine the colors, and get the average of these colors. Sometimes a sample of thousands of triangles is taken at the same time. Some of them might collide or be overlapped. To know which color to sample, the depth map is used. It determines the color to be sampled in each fragment. If you want to explore more about this topic, here are some very important concepts at the time of rasterization. I think we are going to cover all them in different tutorials. Just know it's too much information for this video. I've tried to sort of illustrate the idea of rasterization. As you can see here, we have the original geometry of this model that I made in Blender. In the next step, we discard the z-axis because it's already processed inside the depth map. Now we begin the subdivision of the triangles and we begin to do the sampling to finally obtain the fragments. Let's go to the last room of this museum, and it's the fragment stage. I don't need to explain much here as I have more than a dozen videos explaining the subject. We are just going to see some interesting examples using mostly the screen texture. The first example is the geometry of a cube in which I am deforming the screen texture using the deformations seen in the previous tutorial. In the following example, we have the effect of an old TV. This effect is from the Godot shaders webpage, and I think it looks really cool. It uses various noise deformation techniques, color channel manipulation, and finally the deformation of the screen texture. In this one, there is a raindrop effect. I didn't correct the scale because I was just lazy, but it looks quite realistic, as you can see. The last example has a blur effect, which I think is very useful to give the sensation of speed, or maybe that the character is under the effects of some substance. This is the end of the museum. There are some missing theoretical and technical things in this small demonstration. It's obvious because the courses about the subject take several hours. But here is one more page explaining the rendering pipeline in Vulkan. Every API and every implementation in a game engine can have a different pipeline. Here Vulkan is quite similar to what I exposed mostly in OpenGL. The selection remains pending, but as I mentioned before, Godot doesn't allow access to that feature. There are some techniques to overcome the Godot limitation because it's really fundamental when creating infinite terrains. In this video you can watch one of those techniques. It is very interesting. I recommend you to watch it if you haven't. Finally, if you want to support this channel so I can keep sharing information and interesting effects, you can do it on Ko-fi or Patreon. I put links in the description.